Hi everybody, welcome to this video on inter-seismic strain accumulation. As you probably know, earthquakes happen when faults become locked and they build up strain, which is then released in a sudden event. So one big question for geologists is to try to figure out how much strain is accumulating along faults in between the earthquakes, and that can help us identify fault sections or specific faults that are loaded and more likely to produce the next earthquake. So as we begin this video, I want to just quickly review the classical earthquake or seismic cycle. And this model is typically broken down into an inter-seismic period when faults are locked. Okay, so here's the fault, it's locked, and the plates are moving past each other at a slow and steady rate that we would call the long-term plate rate. As the plates continue to move and the fault stays locked, we develop what's called a slip deficit. In other words, the amount of slip that would have been occurring along this fault, if it was moving freely, is called the slip deficit. So it's essentially equal to the plate rate times time. We also think about another concept of elastic strain. So as these plates move freely, the rock around the fault is actually being squished and compressed and loaded like a spring. And we call that elastic strain accumulation. Now, this all builds up to the co-seismic event when the fault slips abruptly, releases that stored elastic strain in an earthquake right here. And that's what causes all of the damage. So that's the conventional earthquake cycle model that's highly oversimplified. One important idea about this is that faults are often thought of having two sections. So in the near surface, we might have the locked section that we just described. However, as you go to depth and the rocks and the fault become hotter, there's less friction essentially, and the fault is able to creep in a ductile fashion. So not only are the plates moving freely far away from the fault, but those plates are actually slipping freely past each other at depth at the bottom of the fault zone. And we'll often think of this as being below what we call the brittle to ductile transition. This is a very important idea because it is this free creep at the bottom of the fault zone, the lower part, that actually localizes the strain onto the locked part. Right? This is a very kind of strong transition between free motion at depth, locked directly above, which really causes a lot of compression and elastic strain right on the fault here. That's what localizes it right in this area. Another important idea is that, and this is important, faults don't actually have to be locked in their upper portion. And the last 20 years of space-based geodesy have revealed that, in fact, many faults have portions that are kind of 100% locked between earthquakes, and then other portions that are essentially, even the upper part of the fault is freely slipping. And so we'll often describe this as the degree of coupling, and often express it as a fraction. So here's an example along the San Andreas Fault, which was studied by Liu et al. From essentially just south of San Francisco down a bit towards the Central Valley. And based on previously compiled geodetic data, especially INSAR data, they create this plot that shows the creep rate along the San Andreas Fault. And we can see that this area near Slack Canyon, just north of Parkfield, actually is creeping at a very high rate and is almost entirely uncoupled at the near surface. Whereas when you come up closer to San Francisco, the Loma Prieta section is almost entirely locked between earthquakes. So again, this degree of coupling depends a lot on the fault properties and sometimes on the orientation of the fault relative to stresses. So all of this gives rise to an important question. If we were measuring plate motion from space using things like GPS stations and INSAR, how do we actually take those measured motions and convert them into useful information, like what is the actual slip deficit? How much strain has actually accumulated? So just to illustrate that, I've got this example here of the San Andreas Fault. That's the red line running down again near the Parkfield section. And each of these blue arrows shows a measured GPS velocity, essentially relative to a stable North America reference frame. And what we see indeed is that the west side of the San Andreas is moving northward a lot faster than the east side of the San Andreas. And so the difference between the GPS velocities on the west and the GPS velocities on the east tells us something about, well, how fast the plates are moving along this fault, but also tells us something about how much elastic strain is accumulating, kind of the degree of locking along this fault. And so with just the data that we see here, we're actually left with more than 2 free parameters. That makes it hard to actually answer that question, right? How much of what we're seeing here, these GPS velocities, is due to the actual plate slip rate? How much of it is due to the actual pattern of locking, the amount of coupling, or the locking depth on this fault? So answering these questions actually requires what we would call an elastic block model. We have to actually take this data and model it, making some assumptions about the crust. So a typical model that we would use, there's many different models that have been developed, and there's a rich literature around this. In this video, we're just going to present one of the earliest and most simple models, and that is a screw dislocation in an elastic half space, first proposed by Savage and Burford in 1973. So first, what is a half space? That's very easy. A half space just refers to some total space that is cut in half by a plane. So that just says, okay, we're going to assume the fault is a plane that's kind of cutting our space in half, and the space has kind of constant properties throughout. Screw dislocation is an idea that's really borrowed from material science or crystallography. And that essentially just means that you have kind of a dislocation that is kind of moving along a plane, kind of layer by layer. So you can just think of kind of a slow and steady break in the material that's essentially keeping pace with the plate rate here. So what does this model predict? How is it structured? Here's its mathematical formula. It proposes that the velocity parallel to the fault, okay, so that's these arrows right here, the velocity parallel to the fault, is given by the slip rate at depth, okay, that's kind of the plate rate, divided by pi times the arctan of x over d, where x is distance from the fault. So that's perpendicular distance away from the fault, and d is the locking depth, actually. So what this predicts is that the farther you go away from the fault, so the bigger x becomes, the bigger that velocity becomes. And likewise, the smaller d is, that's going to change the length scale. So the more quickly we're going to accomplish the recovery of that full velocity as we move away from the fault. So we can see that indeed d, or locking depth, is a very important parameter here. And I want to illustrate that with a couple of simple models. So what we have here are 2 plots of fault parallel velocity. So that's v in the equation. And this is distance from the fault on either side. And these are actual GPS stations nearby the San Andreas Fault. And so what we see here is if we make our prediction using a locking depth of 18 kilometers, that's pretty deep, we get an excellent fit to the GPS stations. So our kind of screw dislocation in the elastic half space gives us an excellent fit here. However, if we reduce the locking depth to 5 kilometers, we don't fit those GPS velocities very well at all. And this is because a shallow locking depth essentially localizes the elastic strain. It has the effect of essentially imposing a lot of elastic strain very close to the fault, and then that elastic strain falls away very quickly as you go away from the fault. And the way I think about that, right, think about what the locking depth is. If you bring this locking depth up very, very shallow, it essentially means that this kind of free motion of the plates, is happening very, very shallow. And so you much more quickly kind of restore your surface velocities to that plate rate. Whereas if you have a deep locking depth way down here, you kind of spread out that locking over a longer distance. Okay, so just wanted to wrap this up with a real example from Vermont 2014, where indeed they took a lot of GPS stations across the San Andreas Fault here and applied this model, and you can see that they were able to create a nice, excellent fit to the GPS stations by essentially toggling or varying these 3 variables: locking depth, slip rate, and kind of fault location or geometry to create a nice fit to the velocity field. So in conclusion, we've shown that plates move steadily at a long-term plate rate over time. Faults slip at this plate rate at depth, but are often locked at shallow depths. That free slip at depth concentrates the elastic strain onto that locked portion of the fault up high. And the pattern of strain as you move away from the fault in a perpendicular direction depends on that locking depth, also on slip rate and fault orientation. And if we have a shallow locking depth, we see that strain accumulation falls away quickly as you go away from the fault. And finally, elastic models can be used to solve for these 3 variables: slip rate, locking depth, and slip deficit.